Hello everyone, and thanks for watching Edupedia World videos. In this video, we begin a new unit of study called Differential Equations. Now we've seen some basic differential equations before. In one of the previous videos, I did a question of the form of we were given dy by dx. Let's say it would be some polynomial x cubed plus 3x, and we might have been given y of 0 is equal to 2, and using these two things we were able to calculate y of x. The first would give us y of x along with an arbitrary constant, and then from this initial condition we would be able to get y of x uniquely. So this, I told you, was called an initial condition, and this relation between the derivative of y with respect to x and a function of x is what is called a differential equation. There are many types of differential equations. This would be an example of a differential equation. If you had an equation of the type of x squared minus 2x plus 1 is equal to 0, that is not a differential equation because there are no derivatives involved, right? This would be a simple quadratic equation. But a differential equation is an equation involving one or more functions as well as their derivatives. Now the reason differential equations are so important is because in engineering, physics, mathematics, we often come across equations in which one quantity is changing with respect to another quantity. For example, in physics, any equation between the force and the position, or the force and the velocity, would be essentially a differential equation because the force is related to the acceleration, which is related to the derivative of the velocity. Any relation between the current flowing through a wire and the charge flowing through a wire would be essentially a differential equation because current is the rate of flow of charge, right? So in real life we often come across quantities which are the rate of change of another quantity. You've been applying the concept of derivatives for a while now, and so any equation involving the derivative is known as a differential equation. Now there are many different types of differential equation. There are many categories. So first we'll try to be systematic and study all the categories, at least learn what the meanings of all the categories are, and then we'll only study one specific category in detail in this course. So one way differential equations can be characterized is as ordinary or partial. I'm just going to write DEs, differential equation, and generally ordinary, we use abbreviations all the time. Ordinary differential equations are often referred to as ODEs. So ordinary differential equations are differential equations in which only the derivative with respect to one variable are involved. So in this case, the derivative is with respect to x. We could add other terms as well, the double derivative of y with respect to x, 3 times the triple derivative, but as long as all the derivatives are with respect to x, it would be an ordinary differential equation. So this is an ordinary differential equation, d2y by dx squared plus 3dy by dx plus sine of dy by dx y naught is equal to 10 is still an ordinary differential equation because all the derivatives are with respect to a single variable x, and generally the solution would be of the form of y of x, y as a function of x. The other category would be partial differential equations, and which are often abbreviated as PDEs. And in partial differential equation, the derivatives with respect to more than one variable are involved. So let's say you have a function z which is a function of both x and y, a function of two variables x and y, something like x squared plus 2y or sine of xy or whatever. You know what a function of more than one variable is. Then an equation of the type of dz by dx plus 3 dz by dy is equal to 20 would be a partial differential equation because the derivatives are with respect to x. Here you have a derivative with respect to x. It could even have been a double derivative, that doesn't matter. right? The double, triple derivative, whatever, is with respect to x. And here you have the derivative with respect to y. So in this equation, you actually have derivatives with respect to both x and y. Hence, this is a partial differential equation. The solutions of partial differential equations are generally much more complicated than those for ordinary differential equations, but fortunately in this course we will only confine ourselves to the study of ordinary differential equations. Now, ordinary differential equations can be further categorized based on their order. So now we look at what is an order of an ODE. Now I'll just continue using the abbreviation ODE, which will stand for ordinary differential equation, right? So the order of an ODE is defined as the highest order derivative present in the equation. So if we take our simple example of dy by dx is equal to 3x plus 5, this would be a first order ODE because you only have the first derivative of y with respect to x. Dy by dx is the first order derivative, right? And that is the only derivative occurring, so it's a first order ODE. If I have d2y by dx squared, which is the second derivative, the second order derivative or the double derivative of y with respect to x, plus dy by dx whole to the power 4 plus sine of dy by dx is equal to 10y, say. Now this would be a second order ODE. Again, notice they are all ODEs, ordinary differential equations. For the rest of this course, we'll only study ordinary differential equations. And here you have the first order derivative of y with respect to x. Again, you have the first order derivative and you have that to the power of 4. But here you have the second order derivative, right? The double derivative of y with respect to x. Now here I just want to make one obvious point really clear. There's a big difference between d2y by dx squared. This is d by dx of dy by dx, the double derivative of y. So if you have y of x is equal to, let's say, x cube, then d2y by dx squared would be the derivative of 3x squared, which would be 6x. On the other hand, dy by dx whole squared is completely different. This is not the same as this thing. This is the double derivative of y. This is the square of the derivative of y. So this is basically dy by dx whole squared. So if you have y of x is equal to x cube, you will have dy by dx, that will be 3x squared, which means dy by dx whole squared will be 9x to the power 4. Very different from 6x. So dy by dx whole square is the square of the single derivative of y with respect to x. d2y by dx square is the double derivative of y. Again, you could have a more complicated equation, d4y of dx to the power 4 plus 6 d2y by dx squared plus 7y is equal to 10. This would be a fourth order ODE. Why? Because here you have the derivative, the double derivative of y, and here you have the fourth order derivative of y with respect to x. You differentiate y with respect to x 4 times. The highest order is this one, so it's a fourth order ODE. An order for right now, for the sake of this course, is only defined for an ODE, right? For an ordinary differential equation. Another way of categorizing differential equations is whether or not they are linear. So we'll have linear ODEs and we have non-linear ODEs. So the linear ODE is the simpler one, and that is the only one we'll study in this course, and that's an ODE in which the function y of x, by the way, we'll assume that the dependent variable is y and the independent variable is x. But if you have a function in which you have dz by dt, and so you could do the same thing, it's just the derivative of z with respect to t, right? So y of x, the function, and its derivatives appear to the power 1 only and not as products. What this basically means is, if you were to think of a linear ODE as a polynomial, it would have a degree 1, right? Now we are not talking about order, we are talking about sort of degree. So for example, if you have the double derivative, if this is a second order ODE, then you will have d2y by dx squared, right? But this definition says yx and its derivative only appear to the power 1. That means you can only have d2y by dx square. You cannot have d2y by dx square whole cube. This would make the equation non-linear. Right? For the linear equation, let's just focus on second order now. You can extrapolate to any order. A second order linear ODE will have d2y by dx square. It will also have dy by dx. It may have dy by dx, and it may have y. It will certainly not have the triple derivative of y, because then it would be a third order ODE. Right now we're focusing on second. So these three terms will occur, and they will only occur to the power 1. That means you cannot have y cube, you cannot have the square of dy by dx, and also they cannot occur as products of each other. You cannot have y into dy by dx. So again, they are all linearly added. So if you look at these two conditions, there is only one way an equation like this could occur, and that would be, let's say you have f1 of x, the first function, plus f2 of x, a second function, plus f3 of x is equal to, let's say, f4 of x. Right. So basically, now these functions in x could be any functions. We are focusing on the derivative. So nonlinear ODE will not focus on them. They are just ODEs which are not linear. So basically, all the derivatives will occur to the power 1, and none of them will occur as products of each other. So let's just say, for the sake of discussing, a fifth order ODE. So fifth order means the highest derivative would be the fifth derivative, and we want it to be linear. So a fifth order linear ODE means you will have the terms d5y by dx to the power 5. You may have d4y by dx to the power 4. You may have d3y by dx to the power 3, d2y by dx squared. You may have dy by dx, and you may have y. Now if this wasn't a linear ODE, you could have any combinations of these. You could have this term multiplied by this term multiplied by the square of this term plus the sine of this term multiplied by the cos of this term. You could have a whole set of combinations. But if it is linear, they will only occur to the power 1, and they will not occur as products. That means there is only one possibility. They will occur as sums, and they will have functions of x as coefficients. So you might have f5 of x plus f4 of x plus f3 of x plus f2 of x plus f1 of x plus, let's say, f0 of x, and this would be equal to, let's say, a function g of x. So an equation of this type, where f1, f2, f3, g of x can be any functions of x, they don't have to be linear, is called a linear ODE. And since it's fifth order, this is the case. If it was a third order linear ODE, we would remove these two terms, and this will be the form of a third order linear ODE. Again, the reason we categorize equations in this form is we can easily solve linear ODEs, but then for non-linear we have to try some unusual methods, so we try to differentiate this. Right. And finally, we have a last categorization, which is a subset of linear ODEs, which would be homogeneous ODEs. So homogeneous linear ODEs. And homogeneous linear ODEs have the property that this term g of x is 0. Right. The RHS basically will be 0. Right. So the form of a homogeneous linear ODE would be this is equal to 0. Now that has an important property, that homogeneous linear ODEs, because of this property, the RHS is 0, have an important property, which is that if y1 of x and say y2 of x are solutions, so is k1 y1 of x plus k2 y2 of x. That means linear combinations of solutions are also solutions. This is not true for the case in which you would have something here, let's say 5 or 10. Why? Because let's say y1 of x, a function, satisfies this equation. That means the LHS is equal to 0 for y1 of x. The LHS is also equal to 0 for y2 of x. So obviously, if you have k1 y1 of x, you put k1 y1 x everywhere. Since it's a linear ODE, you do not have any squares, k1 will come outside. right? If this was the square, then you would have k1 square outside and this would not be valid. But for a linear ODE, if y1 of x is the equation, is the solution, you replace it by k1 y1 of x, you simply get the whole LHS multiplied by k1, and that is also equal to 0. Similarly for this, and if you add the two of them, they would also give you the LHS 0. Now if here it was 5 instead of 0, then it would be 5 for y1 of x. Then if you take 3y1 of x, it would not be 5, it would be 15 because the LHS would be multiplied by 3. So this particular property, that a linear combinations of solutions is also a solution, a linear combinations of any previous solutions is also a solution, is valid for homogeneous linear ODEs, and that is why we categorize them separately. I'll give a brief recap of everything we've studied till now. First you have ordinary and partial ODEs. And partial DEs, differential equation. Now these will be referred to as ODEs, and we can further divide them based on their order. So you can have first order, second order, third order, and so on. Another way we could categorize ordinary differential equations is by looking at whether or not they are linear or non-linear. And linear ODEs can be further divided into homogeneous and inhomogeneous. Now in this particular course, we will focus on the very simplest case. We will look at linear ODEs that are of the first order. We'll look at both homogeneous and inhomogeneous, but basically we'll look at a few more first order ODEs, but they will be special cases. At the end of this chapter, you should be able to solve every first order linear ordinary differential equation. Ordinary first order linear. I would really suggest you look at these definitions once more and really understand and memorize what they mean, because I'm going to be using these terms again and again, and it would be really helpful if you would immediately know what exactly I'm talking about. For example, when I say a second order linear inhomogeneous ODE, then you would immediately know that it's a linear ODE, but linear combinations of previous solutions are not solutions because it is inhomogeneous. Right. In the next video, we'll look at a few more properties of some differential equations. Thank you.